Good day. We are looking at 92 Voltaic Cells, a sheet that you should have in your package. And it's the kind of question you're going to run into a lot. You'll be given chemicals and you'll be asked to draw a cell. And sometimes you have to figure out if it's electrochemical or electrolytic. But in this case, it's going to be electrochemical with a positive cell potential and therefore produce electricity. And we want to label these kind of things on it. So we have this cell notation. Often you have to draw this part yourself, so you want to make sure the salt bridge goes into both solutions, same with the electrodes. And we have to identify what our cathode and anode are. Silver on our table of reduction potentials is above cadmium, so silver is going to be a cathode, and cadmium will be our anode. There's the reduction of silver. Reduction always happens at the cathode. And we look it up, it's plus 0.80 volts. Oxidation always at the anode, we have to flip the sign, and that's why it's plus 0.40 volts. Now our overall reaction from the two half cells is we had to put 2's in front of the silvers to balance the charge, overall charge left and right, and no surprise there, because we had 1 electron here, 2 electrons there, and that's what we're doing when we balance redox. We're balancing electrons. Now, once we've done that, we know electrons always go from anode to cathode. So they're going to be heading to the left because they're generated at the anode. So electrons, we can see here, are produced there, and they get pulled over by the silver. The silver wants those electrons. And so things that we should think about labeling are, we can put silver ions right in here. That's supposed to be an Ag+. Don't really care too much about the nitrate. It's going to be a spectator. I'm going to have Cd2 plus ions right here. This electrode we said is the cadmium. And this electrode is the silver. And we know this is supposed to be an arrow going that way. Silver's going that way. And the cadmium ions are coming from the electrode. So that's a pretty thorough job. We might have a salt bridge and we'd show that the positive ions are coming towards the cathode and the negative ions towards the anode. But that's what you're normally going to be drawing for electrochemical cell. 2 half cells, salt bridge that connects them, external wire showing the arrow. The next diagram has a porous cup. And all that is, it's acting like the salt bridge. It separates the 2 half cells. So we'd have solution inside here, and we have a solution outside here. And this will prevent the buildup, polarity buildup of ions. Platinum is an inert electrode, and we have to go looking for iodate, and we find it high up on the chart. So it turns out platinum is going to be our cathode in this case, and zinc will be the anode. So zinc is going to be oxidized into zinc 2+. We don't know which electrode's which, so we're just arbitrarily going to label them. So right here, we would say, hey, this has to be our platinum electrode, and this electrode has to be our zinc electrode. So we have our cell potentials. Remember, we have to flip that sign around, and we get a nice 1.96 volts. So that's a fair amount of oomph. We know electrons always go anode to cathode. So again, our electrons are going left because we labeled the cathode on the left. It actually doesn't matter. We could flip the things around. We can't really show that we'd have IO3 minus and H plus in here. That's hard to say. But we can show that we would have Zn2 plus ions right here. And so we would have them for starters, but we'd also be adding zinc ions as the zinc oxidizes. So usually we're not going to ask you to draw a porous cup because it's just harder to label. But understand it works the same way. We have 1/2 cell inside the porous cup and 1/2 cell outside the porous cup in the beaker. Well, that's it.